Okay, this seems to be recording.
Victor.
Yes.
Thank you.
Okay, so you see the record button? All right, so going back, we just began this, and we're going to talk about four major themes pretty quickly. Data description, hypothesis testing, correlation, prediction. There's so many slides, I don't want to spend an equal amount of time with each one, but let's focus first on data description. Before we can do anything, we have to really look at our data. That means you're going to have a spreadsheet in SPSS. Now, I know there are other spreadsheets out there. There's Excel and so forth, but we use SPSS, and the first window that we encounter in SPSS is the data window. Excuse me. So the first window we encounter is the data window. We have to look at our data, and then we begin to use some of SPSS's features about frequencies, counts, and percents. This is going to help us to decide if we have missing data, bad data, data that is simply wrong, if we have outliers. It helps a whole lot in the very early stage to begin to make column, pie, or bar charts. So we always begin our analysis looking at the data, making sure that these guys are in good order, because it's easy to have something that's wrong. Look at it, kind of scan it, see something that's there, shouldn't be there, fix it now. It will only carry forward and be more of a problem later. So this is data description more. Okay. Now, hopefully at some point, you've had a statistics course that covers stuff like this. This is the bell-shaped curve. It's normal distribution. And you see why they call it that. It looks like a bell, although kind of a strange bell. And what we are looking at here is 100% of a given population. So let's say, for example, that we were looking at a tree, and we notice a tree has 10,000 leaves on it. And let's say, because we were bored one day, we measured every single leaf. And we put them into this distribution. So that way down here, this guy here might be the really smallest leaf. And over here would be the really biggest. And most of our leaves would fall in this area. Now, what is this? Because this is a normal distribution, the mean is the average, we're setting this arbitrarily at 0. Of course, that wouldn't be true for leaves, but we're saying a mean of 0 with a standard deviation of 1. This is a theoretical distribution. So if we follow this white arrow, this covers one standard deviation in each way. Or another way of looking at it, we add up to 15% to 19, and then we double it for the other side. One standard deviation across represents 68% of the population. If we go a little further out, if we now go 2 standard deviations on each side, now this represents over 95%. Well, so what? The important thing here is these words: a z-score, a standard deviation, cumulative percent. We run upon this frequently, that if we are looking at a two-tailed test, and by the way, tests will either be a one-tail or a two-tail. This, if we were to look at both sides, we have a two-tailed test. If, on the other hand, we only are concerned about one side, it's a one-tailed test. So the question is, in this model, what lies outside of the 95%? And it turns out to be that the 95% is 1.96 standard deviations across, plus and minus. In other words, it's from right here to right here. Not quite 2, but almost. But on the other hand, if we're going to look at a one-tail test, just looking at this side, then we're not going to care about this, but we're going to say that it's 1.65 standard deviations per one tail. Now, I don't expect you to actually remember this stuff, but you're going to come up, but do remember these numbers. You're going to see them a lot, and you're going to say, where did that number come from? I remember from once upon a time, this number defines the z-score of whether it's 95% or 95.44% or whatever. Okay, that gets to be heavy. So here's the important part summarized. The cumulative percentages that live under the normal curve, plus or minus 1 standard deviation, 68.26% of the population. Plus or minus 2 standard deviations, that's 95.44%, but that's too much. We just want 95. So it turns out that 1 plus or minus 1.96 equals 95% even, it's right on the nose, of the population if it's two-tailed. But if it's a one-tailed, then that 95% lives in 1.645 standard deviations. We care about this. We care about this because we're going to see this significance. So in other words, we are significant in our testing. If the p-value is less than or equal to 0.05, it lives to the right of this or of this. Okay? This is important to know. What we do in statistics is we test hypotheses. And by now, I don't know where you're at in your program, if you have begun to write your research question or not, but part of your research question is going to be the hypothesis. And of course, SPSS, again, this is our academic standard. You do not use Excel, although Excel has its merits, it's not good for this. So I just reviewed a prospectus where the learner did not use SPSS, and you cannot do it in Excel. Well, what we're doing in hypothesis testing is we come up with a thing called the null hypothesis, and maybe you've already encountered that. But what's interesting about the null, it's a straw man. We set it up to knock them down. Our goal is to reject it. See, it's a kind of like backwards thing. We say, well, we don't expect anything to happen. That's our null. Meanwhile, we're snickering behind our back saying, yeah, but we really want something to happen. So we say we want to accept the null, but in reality, we really don't. Okay, if the p-value, the significance that we're talking about, that back there with the bell-shaped curve, if the p-value is greater than 0.05, then remember what we are, we're back further, maybe not that far. Okay, p-values are down here. This is what we're talking about. So what we're saying is if the p-value takes us into the middle zone, in other words, it's greater than 0.05, then we reject the null hypothesis, or it's less than 0.05. False positive, false negative. Now here's the thing. Here's the thing. We cannot ever be 100% sure that our estimate is going to be correct, because there's always going to be a probability of error. So the question is, how much error are we willing to risk? A false positive is, you say it is, but it really wasn't. So when we set the p-value at less than 0.05, we say, in effect, that we're accepting 1 chance in 20, because that's what 0.05 would be. We're accepting 1 chance in 20 that our result is not really true. The other side of the coin, though, is a false negative. That's when you say something was not, and it really was. Okay? Both errors have to be minimized. But that's what we're doing. We're trying to avoid false positive, false negative. We do the hypothesis testing frequently, but by no means always, with tests between the means. There are several: a z-test, a t-test, an f-test. Here's the difference between them. In all cases, we're looking at the difference between means. Now, if you have a population, subjects or sample size greater than 30, and you know what the standard deviation, that little squiggle here, this squiggle, this is sigma. Sigma is the handwriting or the notation for standard deviation. You got something like this where your size is above 30, you know the standard deviation, z-test can be used. If on the other hand it's less than, and the standard deviation is not known, then you use the t-test. And finally, this is here, this little guy looks like a U, that's mu. Mu stands for mean. If you got 3 or more means, in other words, 3 or more groups, then it's F-test. Now, when you use SPSS, this will help you with this. It will help you select. So you're not totally out there trying to figure this out on your own. Okay, interesting little slide. This one here requires a little bit of thinking. On the one side, we got the null hypothesis, which is either false or true. Now remember, this is the null. And here's our decision. Do we accept it or reject it? Now, if our probability is greater than 0.05, in other words, say it's 0.09, we would reject it. So our decision is the null hypothesis is true. And of course, ultimately, the alternate hypothesis is not true. But remember, we're always working with the null hypothesis. That is what we're testing for. So here we go. If the probability p-value greater than this, then we say, okay, it's true, the null hypothesis is true, correct decision. On the other hand, if it's less than 0.05, we say we will reject the null. We reject it. And that means if we reject the null by default, we accept the alternate. Now the risk here is that type 1 error, the false positive. We minimize the risk, okay? Minimize the risk by decreasing alpha, the significance level. And what this means, if we were to say, okay, we're going to set a standard not of 0.05, but say 0.001, well then that's a higher standard, and that further minimizes that risk of a type 1 error. But the problem is, if we were to set our program for 0.001, that increases our sample size greatly, and that becomes sometimes not workable. All right, likewise, if we say, now probability is the power of a test. We'll talk about that later. And this is the chance of committing or not committing a type 2 error. Let me just say one thing about power. If we have a sufficient sample size, and that's really the key, if we have a sufficient sample size, we'll have more power, and if we have a null hypothesis that's declared false, that would be a correct decision. We commit the error of having false negatives when our sample size is too small. Okay, how does this work under the hood? Well, this has probably already been discussed to some degree, so I can pass that pretty quickly. This is, again, the very important model that we're looking at. And last time, I think, we just want to look. If we fall out here, this is the significant zone. If we fall here, this is the non-significant zone. Okay, we always compare our results against an existing distribution. This, I'm sure, is almost never covered, but most people don't know this. If you were to do a t-test and you compare the two, your result is going to be a t statistic. But then what does that mean? How do we convert the t statistic into a value? It is then placed up against a t distribution. Same thing with chi-square. And we'll talk about chi-square coming up. The chi-square distribution is different. It's highly skewed, right? It's highly skewed. So our results have to be measured against this distribution. So the takeaway here is the results of our data are always measured against a theoretical probability. Okay, it's always taking our data, we compare it against a theoretical. All right, moving on. If you've done any work with statistics at all, and you'll see this in the SPSS, it'll give you an output that will tell you or ask you for degrees of freedom. And even, if you've ever heard of degrees of freedom, just raise your hand. I won't see you, but degrees of freedom are out there all the time, and they're widely misunderstood or not understood at all. What does it mean? Well, it is a little arcane, but the definition, degrees of freedom, is the number of values in a final calculation of a statistic that are free to vary. And that means nothing. What in the world that means? It's better understood by illustration. Suppose we are talking baseball. Okay, we got 9 players. There's 9 positions they can occupy. And we have a coach. Now, the coach can, and let's say we're not worried about their particular skill, the coach can assign any player to any position. He wouldn't do that, but he could. He's the coach. So he can tell the pitcher, you go play shortstop or whatever. The coach is free to assign any player. But once he's filled 8 positions, he's no longer free. That last position and that last player have no choice. Therefore, his degrees of freedom is n, that's to say 9, minus 1, or 8. All right? You see where that's going with that?
Yeah.
Because how many values are free in the final calculation? In his, he had only 8 degrees of freedom. All right, take another analogy. And we've all seen this or done this. You got a wire, and you take 8 jewelry beads that are going to be strung on this wire. Okay? Now, these beads, and here's where it's not like real beads, these beads are free to change places with each other. Now, in reality, they can't. But let's imagine they could. The beads are free to move anywhere on the wire. However, the requirement is that the wire must be suspended above the ground. The left hand holds a bead. The right hand holds a bead. How many beads are free to move now? 6. So in this case, degrees of freedom equals 6. Now it's n minus 2. All right, that's what degrees of freedom are all about. Clear as mud. P-value. Okay. This is the dichotomy of significance. And it's typically set, I spoke about this before, 0.05. Means that 95% lies on one side, and it's the extreme, we want the 5%. We're going to say that 5% is the probability that the result is not chance. So this p-value, criteria, significant, non-significant. And again, we need to remember, back several slides ago, it equates to this, 1.96 or 1.645. And again, we have to avoid the type 1 error, okay? Have to avoid that type 1 error. Now, p-value is highly sensitive to sample size. Here's why. The more subjects you have, the more accurate your p-value will be. It can be greatly distorted with a fewer n, with a fewer subject number. So it's sensitive to that. Here's a visual. And I like people sometimes to think in terms of visuals. If you are going, what does a t-test look like in your mind? There's a lot of numbers, but what's a visual? The visual is 2 distributions. And the question is, do they hang out together? So in other words, if this guy here, this alpha, if this alpha crosses into this blue territory, we can say that they're really the same, or they're equal enough. Here's an example. If I was to ask you, what is the difference between a pineapple and an apple? You say, well, the difference is huge. But I could say, they both have apple. If I was to measure pineapples, the curve would be way over here. And if I was to measure apples, curve would be way over here. Huge difference. They wouldn't cross over at all. But if I was to take 2 varieties of apple, let's say Macintosh and Rome or whatever else, they're going to be different, but is that difference really that great? And the answer would be no. So this is a visual for z-test and t-test. Here's a visual for ANOVA. And it's the same idea, okay? Are the tails crossing into each other's territory? Okay, let's look at this guy. His tail crosses into the number 2 and touches into number 3. So it could be argued that these 3 are equal in essence. But notice that his number 1 does not cross into number 4. So in this case, number 4 is dissimilar from number 1. Now, does number 4 cross into number 3? Yes. Does it cross into number 2? Yes. But it doesn't cross into number 1. So number 1 and number 4 are different. And that's what ANOVA is going to look at using an F-test to see if the variance is the same. We're looking at variance. We're looking at tails. All right. Now, as I mentioned, I teach a course in multivariate statistics. And I ask, and basically the course is designed for normal data. What's normal? Bell-shaped curve. If you want to know what normal looks like, go back to the slide with the bell-shaped curve. The course focuses on normal data. And I ask the students, what do you do with your data if by chance your data is not normal? In other words, it's lopsided. And I've had all kinds of interesting answers, everything from get more data to throw it out. And the answer, of course, is you can't always get more data, and that might not even help, and you can't even throw it out, because then what are you doing? What is non-normal data? This is what it is. It has 2 qualities, or it has no mean. In other words, it doesn't have an average. Or it is so highly skewed, in other words, lopsided, on its curve is lopsided, you can't use normalcy testing. So, therefore, if there's no mean, what do? You use the median. And I'm sure you've run across that. What is the median? The median is the 50th percentile, and it is, as I like to say, the honest average. The honest average. Because in a true normal distribution, the mean, that is to say the average, the mode, the most frequent, and the median, 50%, are all going to be together. But if you don't have a mean, you have to use the median. If you don't have a mean, you got to use quartiles, the 25% blocks. And instead of normal distribution curves, we use box plots. Now, this is important for me to point out right here. Non-parametric. Parametric follows the parameters of mean and standard deviation. Non-parametric testing always occurs with ordinal data. Always. That's because ordinal has no numeric quality. Now, I know in the Olympics, they're going to say first, second, and third, and they give them, bronze, silver, and gold. If we say in our ranking, and this happens with Likert. Likert is ordinal data. When we say first, second, and third, we could just as easily say red, yellow, and green. Because what we're doing is we're putting them in a rank, and the rank is arbitrary. To do parametric analysis on this is meaningless. For example, what is the average zip code? Well, I don't know, someplace in Kansas, but it's meaningless. See, because zip codes are not real numbers. They're codes. Okay, and here's the other thing that's important to remember, is that most real-life data is not normal. It really isn't. We would like to think that it is, but it really isn't. Okay, so we have to be prepared to do non-parametric testing. This is what non-parametric would look like. Okay, see how lopsided it is? This is no bell shape here. Okay, so this is not bell shaped at all. And here's the median. Yeah, it's going to be up there. It's 50th percentile. Now, fortunately for us, we have our friend SPSS, who will do the non-parametric analysis for us. So that's the good news. And as a matter of fact, in some cases, it will default. In other words, if you say, I'm going to use a certain test, and the test fails the condition for normality, it will default to a non-parametric output. These are box plots. I'm sure you've seen them. These are not like the curves, though, that we looked at before. These guys are showing quartile. 0, 25, 50, 75, and 100. All right, so the question is, does this line intersect this area here? And in this particular case, it does not. So the non-parametric analysis would say there is going to be significant difference. All right. Chi-square. I think chi-square needs to be in everybody's toolbox. I think, chi-square was taught, at least for me, back in high school. It's a way of comparing percentages. And it is automatically already a non-parametric test. There's no parametric equivalent at all. What chi-square does, it asks the question, is the frequency of groups the same? Are they essentially the same? In other words, is the frequency of men and women in terms of political party membership, is it the same? If there's a difference, is it a statistically significant difference? Well, it goes back to the chi-square distribution and ask that question. The thing with chi-square, as it gets bigger, is it will say, yep, there's a difference, all right. And then it says to you, go find it. Well, because its job is just to say, somewhere in this matrix, there's a difference. You will have to use post hoc testing for that. There are several tools. Those like Bonferroni will tell you where the problem or where the difference lies. This is a visual of chi-square, okay? This particular study, we're looking at age and no age, males and females. What is the relationship? Now, this is just the data for it, hasn't run yet, hasn't given us the results, but this is how it's set up, like so. Here's what I really need to preach about, variables. The rest was kind of didactic. Variables are kind of my core area. As I review papers, that's to say proposals and prospectuses, it is almost always upon the variable that it falls apart. I see a problem with variables almost always. If you don't get the variable right, the rest will fail. You cannot have a meaningful test with meaningless variables, okay? You have to know your variables before the test begins. And I know how excited we are to hit that test button with SPSS without checking the nature of your variables. Know your variables. And here's the thing. If you don't understand your variables, don't expect your reader to. You have, as a writer, as the chair, you got to know these variables. What do they mean? So this is what I'm getting at. You must correctly identify independent, dependent, and possible confounding variables. All right? So an independent variable, a dependent variable, if you switch their position in SPSS, you will automatically screw it up. Automatically, for most cases. You have to know the difference. Who's dependent, who's independent, and especially the confounding variable. You know what? Confounding variables are all over the place. Suppose you wanted to make a test of gender versus job satisfaction. But you happen to also know the years of age and the years of employment. The years of age and the years of employment, those can change your results. If you just look at, are you happy? Are you male, female? You get one result. But if you modify it and take into consideration you have some experience under your belt, that could change things. Okay, you must correctly identify their nature. And what do I mean by that? There's 4 possible types. They are ratio, interval, ordinal, and nominal. Essentially, you can kind of combine in your mind ratio as R-A-T-I-O and interval. They are continuous, but nominal has the word name in it. Gender, for example, that's a nominal variable. Ordinal, we spoke about, that's ranking. First, second, third, whatever. If you don't get that correct, you'll screw it up. Number 3, you must know their relationship. By that, when you do a test, you'll be asked, is this an independent event or a dependent event? And that is not the same. Their relation, the event, I think that's going to be shown on the next slide. Yeah, right here. The relationship is, are you an independent or dependent event? This is not the same as a dependent, independent variable. Let me explain what that means. You're doing a test, and you got 2 outcomes. If outcome A can happen at any time in your process, and outcome B can happen at any time, they don't require each other, those are independent events. But if outcome B needs outcome A, then it is dependent. For example, you do a before or after study. Were you happy with the product when you bought it? That's outcome A. Were you happy with your product a year later after you bought it? So in other words, these are tied together. You cannot do B without A, nor can you do B before A. So you have to remember that. And never, ever confuse variable and event. Okay, let me go back here to identification. This comes from my multivariate class where a student was saying, I can't get this independent, dependent stuff. And I wrote back and I said, easy peasy. 3 words. What predicts what? The guy who does the predicting, he's the independent. The what is the dependent. All you have to do is simplify it to that. All right. And the other part here, distribution. And by that I mean, are we going to be normal or not normal? That's why you have to make, way back in the beginning, I said, know your data, graph it out, take a look at it. Have some idea, what does your data look like? Still more. Watch out for noise. And, okay, noise happens a lot. Almost everything except when you're in a lab condition is going to have noise attached. And in a medical situation, in a, like I said, in a chemical lab, a biological lab, all other variables are going to be excluded. So you have only the test and the control. But in social sciences, there's noise out there. What is the noise? Socioeconomic status, for example, part of the country you live in, your age, the number of years you went to school. Do you or don't you have children? All these things affect outcome. You're doing a survey, for example. There's going to be noise attached with that because hidden in the background are beliefs and understandings and where the people come from, so to speak. Oh, well, that's the other thing. Where do you come from as a subject? Do you feel the same in one state as another? Here's an example. One of the learners was struggling with a concept and it just wasn't working. So I suggested, why don't you do something preemptive? Do a survey in advance and survey restaurant owners to find out what their anticipated experience will be if they raise the minimum wage. Okay, so we're talking fast food restaurants, we're going to talk to the managers, we're going to find out in a state that does not have a raised minimum wage, what effect you think that's going to do to your business. Now, that's going to be different from, say, another state, maybe where there already is a mandated minimum wage. So if the people in California might answer the question one way, the people in Illinois might answer another. That's noise. So you have to eliminate as much noise as you can. So if you're going to ask about the minimum wage, you better ask it of the same group. Keep it to the people who share that experience. Okay? The big noises are covariates. And this can be factored in as ANCOVA or MANCOVA, so forth. Okay. Age of subject in a hip-hop music appreciation study. It's going to be a covariate. I don't know many people my age who like hip hop. Maybe there are. I don't know. Okay, moving on. I don't even know what it is, actually. All right, correlation. Correlation. As I read proposals and prospectuses, everybody wants to do Pearson's R. And just about everybody does it wrong. And that's because Pearson's is not as simple as it looks. And here's the thing about it. It has 6 assumptions, not 1, 6. Both variables. Now remember, this is going to be it's going to be an XY type thing, or YX. Both variables are interval. Okay? Have to be interval. Second, the data, going back to your data sheet, and that's why I was kind of emphasizing that at the beginning, going back to your data sheet, the data has to be in pairs. In other words, your X and your Y have to live on the same data sheet. They don't have to live together, but they have to be on the same data sheet. For every X, you got to have a Y. Next thing, and this again, you go back to my earlier slides, you're looking for outliers. You have to adjust those outliers. You got to find out about them. Outliers will kill you. Number 4, the variables are to be normally distributed. How do you know they are? You're going to go back to my data sheet way in the beginning, and you're going to run some basic graphs. Next, they have to be linear. And finally, I love this word, and I can barely pronounce it. There has to be homoscedasticity, which means that the residuals. Now, what's a residual? When you draw a trend line, almost none of the dots will fall on the trend line. The distance from the dot to the trend line, that's the residual. But the shape of the residual has got to be about the same for both variables. I'll show you a picture. Okay, let me go back to this. Here, both variables are interval. It's got an asterisk. Here we go. In this case, you got to use Spearman's. Spearman's will allow you to have just about any kind of variable. You can have one ordinal and one continuous. You can have both ordinal. Spearman's is very forgiving. But the problem with doing everything by Spearman's, you say, well, if it does everything, let it do everything, it requires a larger sample size. And it doesn't quite have the power. We call that robustness. It doesn't have quite the same robustness. When Pearson's R works well, it is a fun, great thing. But you got to remember, it's not one size suits all. Here are some examples of what it looks like. The top 2, this guy and this guy, these are Pearson's. And that's to say the information fits the model. Okay, this is the trend line. Okay, notice the distribution of the variance. Okay, the homoscedasticity. Likewise here, same, pretty good. This down here, this is Spearman's. Again, we're violating. See these conditions up here? We violate these conditions down here. Okay, the homoscedasticity is way off. Likewise here, way off. So this is the default. We go to Spearman. Now, there's nothing wrong with doing Spearman, except it's not as much fun as Pearson's R, and it's not as robust, as I said. But that is your non-parametric alternative. This also comes from the lived experience of looking at various prospectus and proposals. Students often think that all they got to do is give me an R. Sounds like a cheer. Give me an R. Well, you need more than an R, because R, which is the Latin or the Roman letter for the Greek rho, that simply shows the relationship between one variable and the other. It doesn't give you significance at all. Let me go back one slide. In other words, there's an R going up here. This does not mean it's statistically significant. As a matter of fact, if you have good eyes, you'll see that it's not. Here's a p-value of 0.002. Okay, this is significant, excuse me. Likewise, this one's significant. But the R can be positive or it can be negative. So if you write your prospectus and say, well, a positive R is a good result and a negative R is a bad result, that's wrong. There's going to be three statistics that will be reported. R, which gives you direction, and this is going to vary between plus and minus 1. You're going to also get from the SPSS alpha. And remember, alpha is just another fancy way of saying p-value. And you're going to get a third one, R squared. Now, R squared is just taking this R and squaring it. Just take this and multiply it by itself. But what that does, R squared gives you the sense, the degree of meaning, okay? So in this particular example, I got an R of 0.35 with a P of 0.0, I think it says, I can't read it, 3, and R squared of 0.12. So how did I get 0.12? I multiplied R times itself. There's your 0.12. Now, what does that mean? R squared tells you the degree that one variable affects the other, okay? So in this particular case, the sense of belonging affects the GPA at a rate of 12%. Is that significant? Literature says no, that's not as significant. Okay, so R squared gives you not just the significance, I would say the meaning of it all. Is this meaningful? So the interpretation is there's a weak, yet significant, positive relationship. A sense of belonging increases, GPA also increases. Now, one of the things I have to caution everybody about is the whole idea of group versus individual data. And here's what happens, and this happens a lot. Group data is when you go to a website and there's a table of data. And the persons who made that website or issued that report, they're going to give you the values in summary, not individually. For example, let me show you by illustration. In this particular study, they wanted to see if the years of education correlated with the attitude towards abortion. Okay? Years of education doesn't correlate, but this, now notice the plots here. And they look at that and say, look at that, my, R equals 0.724, fantastic. And I look at it and say, meaningless, because it's aggregated. Because, look at this, you take that same data, and now it's at the individual level. Okay, now we got every one of these people in there, and we do the same thing. So here we got hundreds of, well, maybe not, I did a couple hundred. Now look at our R, and we say R is equal to 0.155, not as impressive. Now it's a positive relationship, but it by no means, and if we go back to the other one, R squared here, it's going to be like 50%, okay? Go down here, it's much less, you know, it's going to be, I don't know, about 2%. Now, I see some heavy marks here. I'm looking here at year 12. I'm looking here at year 14, and I'm looking here at year 16. Now remember, this is years of education. What happened in year 12? They graduated. What happened in year 14? They graduated from community college. What happened in year 16? Not everybody. In year 16, they graduated from college. Okay? That's why you see these clusters. Once again, I have to continue to tell you, visualize your data. Do plots. Have scatter plots. Know your data. Don't just jump into an analysis. Okay. Prediction and correlation, they're associated. Not quite the same thing. Prediction predicts. Regression models, typically they're linear. They can be multivariate. They can be polynomial. The one that we encounter most is linear regression. However, that is not by any means the only regression model you'll have. Linear is a good place to start. Okay, this is a subject for a higher course, but there are other types of regressions. Let me just show you. what I mean. This is simple linear, okay? And here's our y and x. This is what we just talked about. Here are your data plots. This is your best fit, least squares it's called. And you know what? You learned that in high school, I hope. I hope you did. Well, I did. This is what they taught us in algebra class, y equals mx plus b. All right? They're saying that for every x, you multiply, well, let me tell you what these things are. M is the slope of the line. Okay? That's the slope of the line. And B is the y-intercept, in other words, where it hits here. If I want to know what a dot way out here is going to be, okay, if I want to know what, so let's say we have an x value way over here, and I want to know what's going to be up here. I plug it into this formula. This is predictive. All right? That's predictive. However, not all regression lines are linear. This guy here is polynomial. If I was to try linear on him, I would draw, excuse me, can't do that. I would draw a line like this. Okay? Okay? And SPSS would be telling me, you can't do that. It's violating the homoscedasticity problem. Anyway, so you look at your data, and I ask myself, what does this look like? What does that look like? It looks like a snake. But I know from, again, you know, the benefit of having some good math courses in the past, I recognize that as polynomial. And I do, now how do I do a polynomial test? I go into SPSS and I click the polynomial checkbox. Matter of fact, SPSS will give me several. It's going to say, do you want to do linear? Check it off. Do you want to do polynomial? Yeah, check it off. You want to do cubic? Check it off. You want to do quadratic? Yeah, why not? And it'll run them all. And then it will give you an output. And your output, and that's not quite the same, but your output's going to be like that. Why is this important? Why is this important? Because something is going on right here, okay? What phenomena is taking place that lowers it here, okay? Depending upon your data, you got to look at that. Is something taking place here that changes everything, okay? Something happening? Or are these guys out? Are those guys outliers? All right? So, again, cannot overemphasize, look at your data. If you didn't look at that, you wouldn't see the polynomial nature of it. All right. We're getting to the end. Sample size. I touched on sample size already, you know, but I see people mess this up too. And here's why. I think by now everybody knows you got to have a sample size. The problem is there are really two types of sample size. Two types. And if you mess that up, guess what you did? You messed it up. So you have to know the difference between your two sample sizes. One is sample size to survey a population. The other is sample size for power analysis. Let me explain the first one. We are probably sick unto death of political polls, but they'll say that they asked 1,027 people out of the whole country, okay? They did a sample size for a survey. And you always spot, you know, when I see a student write, well, my confidence level is going to be this. And I think, oh, no, that is the wrong sample size. I spot it right away. Because what you want is this guy. Sample size for power analysis. And by the way, I did not put this down on the slide, and I should have. There's a software out there, and please write this down. It's called G-Power. And G-Power is fantastic. It comes out of Dusseldorf, Germany, but it's in English. It's an extremely powerful software. Find it. Because, see, remember I spoke about those test type 1 and type 2 problems. This software, G-Power, will tell us how many subjects we need. Okay, now of these two, yeah, there are times you need them both, but know the difference, okay? Here's G-Power. Okay, now in this particular, you know, it's not, I'm not saying this is easy, and, you know, but it's what it is. Here, we're asking a question. How many do we need? And here's our answer right there. We need 64, okay? We need 64. But how do we get there? Well, we said, okay, it asks us several questions. Let's start with this question first. What type of test are you going to do? You got to check a box here. You got to know what type of test you're going to do. If you choose the wrong one, guess what you did? You messed it up. You got to know the type of test. Then you have to know the type of power analysis. This is pretty easy. Here you're doing a priori. In other words, you're looking for a sample size. You can also do this post hoc. And by doing a post hoc, that will tell you what your power was after the test is run. But here we're looking ahead. We're looking a priori. All right, we're choosing number of tails. And again, way back in the beginning, I told you about tails and their importance. In this case, we're going to choose one tail. In other words, we don't care about what's going on down here. We only care about here. And that changes the critical value. It changed it now to be 1.645. Okay? That's right here. Effect. Effect is the measured difference between our means. Okay? This is this doesn't have a metric attached to it. It's just a number. It's a ratio number. We have several choices. And the choices depend upon the type of test. If we choose 0.1, we're saying this is a small effect, boy. We're not going to, we got to look at a lot of people to detect this. A 3, medium size, middle of the road type thing. If you did, say, 0.5, you say, oh, you know what, that effect is going to be pretty large. It's not going to take that many to do it, okay? So you have to choose it. And again, choose something. The alpha, remember what alpha is, that's p-value. So you're going to say, all right, what p-value am I going to be happy with? And you say, I'm going to be happy with 0.05. I'll just throw it in. Last question. It's going to say, how willing are you to be right on your negative? And you're going to say, you know what? I'm happy if I'm right 80% of the time to not commit a false negative. And that's at 0.8. You do all this, and then, now's the fun, you hit the button. And pow, tells you 64. And it tells you degree of freedom. We learned about that, okay? So that's G-power. Look it up, find it. If you don't have it already, it's a great little thing. It's free. I don't know if I told you that. From Dusseldorf. Good folks. Okay. Well, all right. I'm not going to preach on this a lot because you're going to get this from your chair. One thing I want to say here, though, is this research question. And I read a lot of them. Essentially, your research question and the hypothesis, they need to have these things in them. I should be able to read your research question and say, aha, that's the IV, independent variable, and yeah, there's the dependent variable, and also possibly some covariates, okay? So, and I like to apply this test. Don't have a situation where you leave too much room for doubt. And we spoke about noise earlier, okay? Noise will create reasonable doubt. Keep it low as you can. Control your variables as much as possible. Eliminate the noise. Eliminate the reasonable doubt. Okay, we're almost at the end. How do you know, after we did all this, I didn't tell you really which test to do for what, because I didn't have to. All I need to tell you is to mark down this website and go there, because this guy, Laird, has a fantastic website. Now, it has a problem, though. He may or may not charge you a fee. The fee is not a lot. So I would, take a look. It's possible, and I cannot verify this, that it is free for university students. I cannot verify that. If it's not free, sign up when you need it. No sense doing it too far in advance. But, I think it's like $5 a month, something like that. So it's not going to kill you because you're spending money like crazy anyway. Laird is fantastic, filled with information, filled. You don't know what test to use? Use that drill down test selector. Just answer the questions. It'll say, okay, this is what you got to do. And then it's going to show you how to do it. And then if that's not enough, it's going to give you a work-along data sheet so you can practice some more. So, you know, if you're going to use it, Laird is worth the money. Okay, last slide. Hooray. Final word. I never came up with this saying, but I love it. And the saying is this: if you torture numbers enough, they will confess to anything. What in the world does that mean? It means that just because you get a result, okay? I mean, you can put the wrong numbers into the box and you'll get something, depending. That doesn't mean this reflects reality, that you answered your research question correctly, that it's meaningful and important. Okay? Garbage in, garbage out. You have to watch the quality of your input. Now, here's the thing, in summary. Someday, somebody's going to read your work, okay? I don't know why, but someday somebody might pull it off of the archives. The last thing you want them to do is make fun of you. And you're not going to know it, but the last thing you want them to do is read your stuff and say, oh, for crying out loud, this is awful. You don't want that. Okay, so now I'm going to unshare my screen and take a look at all of you guys. Ah, a good-looking crowd you are indeed. So I know that the chat room has been busy, and now I'm going to, Melissa, would you like to discuss some of the chats? Have you been, okay, Melissa, yes.
Sure. Actually, there wasn't anything that really was remaining, Dr. Landry, for you to answer. Dr. Lane had some requested some information. And then a link to the G-Power, which you had used, which we recommend that most first students use for determining power if they don't have another source to use. So I included the link for that. And as Dr. Landry mentioned, that is a free resource. So very user-friendly. The user guide is extremely helpful, and like we said, everything is in English. And then the Laird website is free for instructors and faculty. And learners, I just had a learner sign up last month, and she said it was $5 a month. So I included that as well as a reference to the CERT, which has some additional resources available for quantitative research and analysis. So
that's true.
Some good information and resources for us all to look at, and that was pretty much it. Your webinar was excellent. I think a lot of really good positive feedback on the quality of the webinar as well.
If I give you one final takeaway, it's this. Make sure your data sheet, at the very beginning, is good. Look at your data sheet. Quality that has to be there will carry through the rest of your analysis. If you don't have quality in your data sheet, you cannot have quality in your variables, and you cannot have quality in your analysis. That's the takeaway. You guys have been great. Of course, I had you muted. Thank you. But great.
Thank you.
You're welcome.
This is Jillian. Thank you so much.
You're quite welcome. We'll find some way to share this with you. PowerPoint is not a problem because that is a relatively small file. The problem is the video, even when it's condensed, this becomes too big to use as an attachment. We can find a way to share both the video and the PowerPoint. With the PowerPoint, definitely, yeah.
So everyone that's in the meeting will get the video?
Okay, I'm gonna, it'll not immediately, give me a chance, but I'll have them available somehow. Okay, guys, thank you.